here's the chapter 12 and 13 study guide. So we're gonna go one by one, and you can ask any questions during our Zoom session. So we're looking at chapter 12, which is relating to concepts of heat, and chapter 13 is related to pressure and Bernoulli's principle. So let's get to heat. Definition of specific heat and units for specific heat. So the definition for specific heat is the energy that's needed So it's the energy that's needed to increase a mass by 1 degree. And it's 1 degree Celsius or 1 degree Kelvin. It's one and the same because it's usually seen in the form of delta T, which is the change in temperature. And the change in temperature on the Kelvin scale is the same as the change in temperature on the Celsius scale. We'll get to the units a little bit later. The formula for Q, which is going to be heat. Remember, heat is measured like energy. It's measured in joules. And it is mc delta T. The amount of heat released by a material is going to be equal to the mass of the material times the specific heat of that material times the temperature change of the material. This is indicating, when it's bold like this is indicating that this is going to be a mathematical one. This is going to be just like the Cheeto example. Actually, we didn't do the Cheeto. We did the cashew. So as part of this problem, it's also going to be converting from joules to calories or kcals. And if you remember, 1,000 little calories is equal to 1 giant C calorie, which is going to be equal to 1,000 or 1 kcal. So 1,000 calories is 1 kilocalorie. 1 kilocalorie is 1. This is what we eat. This is the edible calorie. So on the food labels, we're measuring actually these calories and not the other ones. And if we're converting from joules to calories, okay, if you remember that we have 4180 joules is equal to 1 kcal, again, or we have 1 of these calories right here. So both of these are related to that cashew problem that we had. Looking at the phases of a heat chart, what particles are doing at each phase and between each phase? If you can draw this over here. If you remember from chemistry, we are going to be increasing, over time, we're going to be increasing the temperature. So we're adding heat, continuously adding heat, and the particles are going to be increasing in their molecular motion. But then if you remember, these are going to be plateauing. The temperature no longer increases, but it stays the same. This is when you have, for example, ice. This is when you would have ice and water. And the temperature is not going to increase until you melt all of your ice. Once melting has concluded, the temperature can increase again. Now we have water. So here we have a solid, and here we have a liquid. And in between are when you have your phase changes, like this. Okay, and this is when we're going to have a gas. If you can number these, 1, 2, 3, 4, and 5. And we're going to discuss what's happening in each of these cases. Particularly, we're going to look at phases 1, 3, and 5, or the stages of 1, 3, and 5. When you have 1, stage 3, or stage 5 in this scenario, what's happening is, in each of these cases, you'll notice that the temperature is increasing, and it's increasing. And we're increasing the temperature because all of the heat, which is Q, Remember, Q is heat. All of the heat goes into increasing the kinetic energy. We have a solid. When you increase the energy, what's going to happen is the heat's going to go into increasing the kinetic energy. The particles are going to vibrate faster. When it's a liquid, they're going to move and rotate faster. When it's a gas, they're going to be colliding with each other faster. What's happening, though, at the stages of 2 and 4 is a little bit different. At stages 2 and 4, these are your phase changes. And all of the heat goes into the phase changes. It's not going to increasing the kinetic energy. So to summarize, what's happening here is we're increasing the heat, it's going into increasing the kinetic energy, and then what happens is it starts to melt. Now we have solid and liquid, and the temperature plateaus because all of the heat's going into the phase change. Once we've melted all the ice, then all of your temperature starts to increase again because we're increasing the kinetic energy because we only have one phase. Then we are up here and we're at a phase change again, and the heat goes into the phase change, so we don't increase the temperature. And now we're starting to boil water, and then after all the water is boiled off, we can then increase the energy of the gas. Looking at the units down below here for heat. Again, heat's measured in joules, and what we have here for mass is we have kilograms. And we have, over here, we have the change in temperature, which is going to be degrees Celsius. Well, if we want to end up with heat that's in joules, that means the units for specific heat that we talked about up here are going to be joules over kilogram degrees Celsius, or degree Kelvin. What's going to happen is the kilograms will cancel, the Celsius will cancel, we'll be left with our units in joules. So that's the first part, and that's looking at the heat. So what's the definition of a fluid, and why solids do not meet that definition? So what we have, fluids are actually liquids and gases. And to meet the criteria for being a fluid, you have to move and flow. Liquids and gases meet that criteria. However, solids do not move, they do not flow, because they are crystals. So they don't move. Definition and formula for pressure and units in English and metric system. So pressure, here's the definition, is equal to force over area. And in the English, we have the PSI, which is pounds per square inch. In the metric system, you have pascals, which is a Newton over a meter squared. And you're going to need to convert from PSI to pascals, just as we did in the foot pressure lab. So if you're given pounds per square inch, we're going to be converting into pascals. So if you remember, when we're converting into pascals, we can convert the inches into meters, but converting from pounds to newtons is a little bit more difficult, because a newton is a kilogram times a meter per second squared. And the kilogram is a mass. If you remember, Newton is a force, and a force is equal to mass times the acceleration. So in converting from pounds, we need to convert to kilograms. Then we also need to multiply that by 9.8 meters per second squared. So we're first going to convert from the pounds to the kilograms. And this is going to be 0.45 kilograms for every pound. So we've converted from the pounds to kilograms, but now we want to get it into newtons, so we have to multiply it by meters per second squared. So we're multiplying by the acceleration, or the gravity, which is 9.8 meters per second squared. This gives us kilograms meters per second squared, or newtons. So we're done with that portion, but now we need to convert the inches squared into meters squared. So we have to convert our inches to centimeters. And 1 inch is 2.54 centimeters. But we have square inches, so we have to square the inches and square the centimeters. So the inches squared has been taken care of. Now we can convert from centimeters to meters. And we have 100 centimeters is equal to 1 meter, but of course this also needs to be squared as well. So this is the work that you're going to be having to show to convert into pascals. Pascal's principle. This is the principle of toothpaste. This is where the force is going to be transmitted evenly through the fluid. You squeeze on one side of the toothpaste tube, it's going to come out the other side. Calculate the force from the hydraulic pressure and the relative displacement. Two parts to this question. Notice how it's not a short answer. It's a mathematical problem. So if you remember, if we have a piston that moves over on this side, and we're attached with a fluid to another larger piston over here, the pressure on this side is going to be equal to the pressure on the other side. So we're going to calculate what's the final output force that we're going to get from this. Get the lights on. Okay. So we're going to start off, since pressure is equal to force over area, I have force over area is going to be equal to force over area. And I want to solve for F2. What's my final force output going to be? We multiply both sides by A2, multiply by A2. To remind you, that means that your output force is going to be equal to your input force times the ratio of the areas. And since the area of the second is larger than the first, our output force is going to be larger. So when we push down with a certain force, okay, we're going to get out a larger force. However, we can't get any more work to do this. When pushing down with a large force, it requires a large displacement. And if you have a larger force on the other end, you have to have a small displacement. We can't get any more work because we have a conservation of work. Bernoulli stated that if you increase the velocity of a fluid, you're going to decrease its pressure. How an airplane provides lift, airplane wing. We discussed this in lecture. The air has to travel over a larger distance on top compared to the bottom. Since it has to go a larger distance, the air is traveling at a larger velocity on the top. And according to Bernoulli's principle, it's going to decrease the pressure, creating low pressure on top, and it's higher down below. The high will want to equalize itself, and it will push up to equalize the pressures. Why cups come together when air is blown between them. Okay, and this is going to be, if you remember, I had a tube or a straw, and I blew the air through between them, and so it was increasing the velocity decreasing the pressure, creating low pressure. Where is it high pressure? It's higher pressure on the sides, and it wants to equalize, and so it pushes the two cups in. You can cross off why liquid stays in a straw and why a ping pong ball stays afloat under a stream of air, and what causes the water to pool. So the last concepts are related to thermal expansion and plasma. So the net effect on expansion of materials when heating and proportional to temperature and length of the object. When you increase the temperature, you're going to increase the length of an object, and it's going to be proportional by the increase in temperature and the original length. You can have two formulas, one involving expansion, linear expansion, the one involving volume expansion. Again, we did the rearranging of these. The change in length is going to be equal to the original length times the coefficient of the solid times the change in temperature. But when you rearrange to both sides, your final length will be equal to the initial length plus all of this, which is how much it's expanding. So here's the original, this is the expansion part right here. So the change of length, this is the expansion. And it's the same thing for volume. The change in volume is equal to the original volume times beta, which is the coefficient for liquids, times the change in temperature. And if you want to find the volume, the final volume, it's going to be equal to the initial volume plus the amount that it expands. Last problem, definition of plasma. Plasma is going to be highly energized gas. Highly energized, or we can say ionized gas. And where to find plasma? You could find it in the sun, lightning, and you got it in the auroras, and of course you have it in neon lights. That's it for a review, and we can go over any questions you guys might have during our Zoom meeting.